In this video, we're going to talk about graphs of equations with two variables and some special points and properties of these graphs. So we have two variables, so usually x and y, and then we often talk about the x and y intercepts and whether or not the graph has any symmetry. Okay, so that's what we're going to talk about in this video. So first, let's think about graphing. Okay, so when we have an equation in one variable, the solutions are just numerical values. So for instance, when we solved a linear equation, we got x equals some number. Equations in two variables, they have solutions that are ordered pairs of values. So you have an x value and a y value as your solution. So these are the things for the graph that we want to plot. Now, attaining a graph is difficult, and throughout the term, we're going to get better and better at it. But for now, we may wish just to plot the points that are solutions to the equation to get an idea of what the graph looks like. Okay, so when you're doing this, what you're going to do is choose an arbitrary value for either x or y. Often we do x because the functions are often y equals f of x, some function of x. So normally you have y equals some equation with x's, so it's easier to plug in x's. But you can pick values for either. Okay, and then we're going to solve for the remaining value. So if you pick a value for x, you're going to solve for y. If you pick a value for y, you're going to solve for x. And then we plot the ordered pair on the plane. Okay, doing this repeatedly can tell us what the graph looks like. Okay, this is not ideal though, because it could be that you just don't pick the right points to see what the graph looks like. You might guess incorrectly. Okay, but for now, that's what we're going to do. So first of all, how do you tell if a point is on the graph? Now, there's a little typo here. This should be y equals that function. So we want to know, is the point 1, 0 on the graph of this function? So what we want to know is, so this is i.e., is x equals 1, y equals 0, a solution of the equation y equals x cubed minus 2 root x. So to figure that out, we can just plug in those values. So remember, your coordinates always have the x coordinate and the y coordinate. So that's why I knew x was 1, y was 0. So if we plug those points in, I'm going to have 0 is equal to 1 cubed minus 2 times root 1. Okay, so that says 0 equals 1 minus 2 times 1, which is 2. So that's negative 1. Okay, so we get 0 equals negative 1. Obviously, this doesn't make sense. So we got something untrue, which means that the point is not on the graph because it does not satisfy the equation. Okay, so that is a point that we would not include on our graph. Okay, so if we tried to graph this function by plotting points, we could make a table of values to keep track of all the points that we plot. Okay, so we have our x value and our y value. And then we might want to graph it. Okay, so there's my y-axis, and there's my x-axis. Oops. Okay, so here's x, here's y, and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so obviously this would be better if we had a grid here. So if we plot some points, so let's say we pick x equals 0. Okay, when x is 0, if we plug that into here, we get 0 cubed minus 2 times 0. So we're going to have y is 0. So we're going to have a point at 0, 0 on our graph. Okay, maybe we pick x as 1. Well, we actually already did x as 1, and we got, we saw 0 was not a solution, so we didn't actually get anything. So if x is 1, this is a different equation too. I should pay attention more. So when I plugged in 0, I still get 0, okay, but I'm plugging into this equation. I thought it was the same as that one, but it's not. Okay, so we're using this equation down here. So when I plug in 1, I get 1/2 times 1 cubed minus 2 times 1. Okay, so that's 1/2 minus 2, which is negative 3/2. Okay, so that means I get a point at 1 and negative 1.5, so down here. Okay, if I plugged in 2, I get 1/2 times 2 cubed minus 2 times 2, so that's 8/2 is 4. 4 minus 4, I get 0. So at 2, I'm actually y equals 0. Okay, so that goes there. Okay, maybe we want to try minus 1. What happens in the negatives? So I'd have 1/2 negative 1 cubed minus 2 times negative 1. So that's negative 1/2 plus 2. So that's actually going to be positive 3/2. So that's going to be up here. Okay, maybe I want to do another. I don't know, negative 2. If I do that, I'm going to have negative 4 plus 4. So again, I get 0. So at negative 2, I'm again at 0. Okay, at negative 3, it's going to be negative 27/2 plus 6, which is negative 7.5. Okay, so negative 3, I'm way down here. Okay, and so you might guess that the graph, okay, if I just sort of connect the dots here, the graph might look something like this. Okay, so that would be my guess. But how do we know? So I made these points the sort of turnaround points, but how do I know that's where they are? Maybe it goes higher and then turns around. Okay, who knows? I just guessed. It would be lucky if I actually guessed the place where those occurred. But we can get an idea of what the graph looks like anyway. But this is why plotting points is not ideal. Okay, now the x and y intercepts of a graph are some special points that are on the graph. Okay, so these are the coordinates, the points where we cross the x and y axes. Okay, so on the x-axis, so that's this axis here, the y value, the vertical distance, is always 0. On the y-axis, so at this point here, the x-coordinate is 0. So if you want to find where it crosses the x-axis, okay, so the x-intercept, that means the y value is going to be 0. So we want to set y equals 0 and solve for x. Okay, and if you want to find the y-axis, the y-intercept, sorry, so this is when you cross the y-axis, that means that the x value is 0. So we set x equal to 0 and solve for y. Okay, so in our picture, we can see that if we go up here, x-intercept, I can't spell today. The x-intercepts, we actually have multiple. So there's one at negative 2, 0. There's one at 0, 0, and there's one at 2, 0. Okay, now we didn't find these. We're just going from the picture. Those are where we have that it crosses the x-axis, and we didn't solve for them, so maybe there's more, but if our graph is correct, then there isn't. Okay, now the y-intercept, there can never be 1 if you have a function, which we're going to talk about later, but okay, so here it's 0, 0. So 0, 0 is actually an x and a y-intercept. So that's this point in the middle here, because that's where we cross the y-axis. Okay, so just to be aware, the intercepts are points. Okay, so you want to think about them as ordered pairs. Okay, which is why I wrote them as ordered pairs. Okay, so the x values for the x-intercepts are the ones that are changing, and the y values are always 0. And for the y-intercept, the x value is always 0, and then the y coordinate, whatever it is, here it happens to also be 0. So I'm going to skip example 3 and do example 4 instead. Okay, so here we want to find the x and y intercepts for this equation. So I'm going to do the y-intercept first. So to do that, we set x equal to 0. Okay, so I plug in 0 into my equation. So 3 times 0 minus 2 minus 0 is equal to y. And I want to solve for y. So 3 times 0 is 0 minus 2. So I'm going to have square root of minus 2 minus 0. It doesn't matter. So y equals square root of minus 2. Okay, this does not exist. I'm just going to write dne. So you can never take the square root of a negative number. So that means that here there's no y-intercept. Okay, so the graph of this equation would never cross the y-axis. Okay, when we want the x-intercept, we want to set y equal to 0. So that means I want to solve the equation 3x minus 2 minus x equals 0. And these are similar to what we've done before. Okay, so this is a radical equation in one variable. So let's isolate the square root. So I'm going to add x to both sides. So I get 3x minus 2 equals x. And now I can square both sides to get rid of the square root. So that means 3x minus 2 is equal to x squared. If I move everything to the right, I'm going to have 0 equals x squared minus 3x plus 2. And now I can factor this. So I want two numbers that multiply to give positive 2 and add to give negative 3. So that's going to be negative 2 and negative 1. So x minus 2 times x minus 1. So this zero product property tells me that that means that x minus 2 is 0, or x minus 1 is 0, which means that x is equal to 2 or x is equal to 1. So those are our possible solutions. Now we should check them because we could have extraneous ones here. So if I plug in x equals 1, I'm going to have square root of 3 minus 2 minus 1. And I want to know, does that equal 0? So square root of 3 minus 2 is root of 1, minus 1. Okay, that is 0. So that one checks out. And then if I try x equals 2, I'm going to have square root of 6 minus 2. Okay, minus 2. Okay, so that's square root of 4 minus 2. And again, that is 0. So both of these are correct solutions. So that means that my x-intercepts here are 1 and 1, 0, the point, and the point 2, 0. Okay, so the x-coordinate can be 1 or 2. Both of those are where it crosses the x-axis. Okay, let's talk about symmetry for graphs. Okay, so we have symmetric across the x-axis first. Okay, so what that means is for every point x, y on the graph. Okay, so let's just draw some function here. Okay, maybe something like that. So here, let's say this is my point x, y. Okay, so for every point on the graph, x, y on the graph, we're going to have the point x negative y is also on the graph. Okay, so x negative y is going to be down here. I'm going to draw this in a different color. Okay, but they're both on the graph, so you can see that it's a reflection over the x-axis. Okay, so if you go over the x-axis, it looks the same on both sides. So that's symmetric across the x-axis. Okay, if we're symmetric across the y-axis, something similar happens. Okay, so if for every point x, y on the graph, okay, the point negative x, y is also on the graph. Okay, so if I have a point, say here, x, y, then I'd want to go negative x with the same y. Okay, that should also be on my graph. So something like that would be like a parabola that is not moved over at all. Okay, so something like that would be symmetric across the y-axis. Okay, now symmetric across the origin. Here, so we have a point x, y on the graph. Okay, now here, that means the point negative x, negative y, so we negate both of them, is also on the graph. Okay, so if I had something like, I don't know, like that, okay, it's going to also need to have something like that. Okay, so let's say this is my point up here is x, y. So that's over x, up y. So we go over x this way and down y. So this is the point negative x, negative y. So if you think about taking it at the origin, taking 1/2 and rotating it 180 degrees, it would land on itself. Okay, so that's what it means symmetric about the origin. Okay, now to verify these symmetries, so to test for them, what you want to do for x-axis symmetry is replace y with negative y, okay, in the equation, and simplify. Okay, if you obtain an equivalent equation, then there is x-axis symmetry. Okay, now to test for y-axis symmetry, you want to do the same thing, except that you replace x with negative x. Okay, so again, if you obtain an equivalent equation, oops, I missed a word here, an equivalent, then you're going to have the y-axis symmetry. Okay, now for the origin symmetry, what you can do is replace both. Okay, so x with negative x and y with negative y. Okay, equivalent, simplify and get an equivalent equation means that you have origin symmetry. Okay, now I should mention, we'll talk about this later, but y-axis symmetry is often called even symmetry, and origin symmetry is often called odd symmetry. So when we talk about functions, x-axis symmetry, we don't actually have a function. Okay, so we're not going to use that one later on, but for now, it's still a type of symmetry, so we still talk about it. But in the future, it maybe isn't as common. Okay, so let's just do one example where we test for all three of these symmetries. Okay, so I'm going to do number 4 here. Okay, so I'm first going to test for x-axis symmetry. So that means I want to replace y with negative y. So I'm going to have negative y is equal to negative x cubed over x squared minus 9. Okay, so then if I solve for y, so I multiply by negative 1, I get y equals x cubed positive over x squared minus 9. Okay, so this is a different equation. Okay, so that means no x-axis symmetry because we got something different. Okay, so now we try y-axis symmetry. So we plug in negative x. So I'm going to have negative x cubed over negative x squared minus 9. So if I simplify that, I get negative. Now negative x cubed is actually negative x cubed because it's negative 1 cubed times x cubed, and negative 1 cubed is negative 1. Okay, negative x squared is actually just x squared, because when it's an even power, the negative is going to go away. So that means I get y equals positive x cubed over x squared minus 9. Again, this is different. Okay, so there's no y-axis symmetry. Okay, we try the origin. That means we're going to replace both. So I'm going to have negative y is equal to negative x cubed over negative x squared minus 9. So that's negative y. This is going to be equal to positive x cubed like we had before over x squared minus 9. And then if I move the negative 1 over, I'm going to have negative x cubed over x squared minus 9. Now this is equivalent. Okay, so that means this y equals negative x cubed over x squared minus 9 has only origin symmetry. Okay, because we got an equivalent expression there. So that one worked, whereas none of the other ones did. So I'm going to leave these other two for you to try, and I will fill them in a subsequent video. But this is how we're going to graph at the moment, and how to find the intercepts and the symmetry for the graph.